In this lecture, we're going to look at indefinite integrals. Now, let's just recall the fundamental theorem of calculus. It said that the integral from a to b of little f of x dx can be obtained by taking an antiderivative of little f, which we're calling big F, and evaluating it at the limits of integration and then taking the difference. So big F of b minus big F of a. So what this means is in order to calculate a definite integral, we need to come up with an antiderivative. And so that's our problem. How do we find antiderivatives? Now, finding antiderivatives can be a challenging task. We're going to look at strategies over the first half of this course for finding antiderivatives, and what we'll see is that it requires good pattern recognition skills and lots of practice, So make sure you're doing lots of exercises, lots of examples to get those pattern recognition skills down so that you can start evaluating integrals by using antiderivatives. What we're going to look at in this lecture is just a basic introduction to finding antiderivatives, and then we'll look at a number of examples where we compute some integrals. But first we're going to look at new notation for, well, a somewhat old idea. We've got notation for derivatives. If I have a function little f, I have a notation for its derivative. I'd like to have the same thing for an antiderivative. I'd like to have a notation. Rather than always writing big F for the antiderivative of little f, or big G for little g, etc., I would like a notation that doesn't involve introducing another letter, albeit capitalized. And here's the notation we're going to use. Due to the connection with the integral, we're going to use an integral with no limits of integration to represent the antiderivative of a function. And we're going to call this the indefinite integral. The definite integral is a number. The definite integral is the one where you've got limits of integral from a to b. The indefinite integral, we're leaving off those limits of integration. That's no longer a number. That now represents a function or a family of functions, the set of all antiderivatives. So we're going to write the integral of f of x dx and say the indefinite integral here, because there's no limits of integration. And we're going to assign that to mean this function big F, which has the property that its derivative is little f. In other words, it's the antiderivative. Now, it could get confusing. We'll admit that. It could get confusing. The notation is going to be used in two different ways. We'll either have it represent the set of all antiderivatives. So that is, this indefinite integral represents a collection of functions, all with the same property that their derivative is little f. Or we may just use it to represent a single function, just one single antiderivative. And it turns out that even though this could be confusing, it's not so bad. Let's just think about what the difference is. If I have two functions, which are both antiderivatives of little f, how are they related to each other? So let's just note that if f of x and g of x are both antiderivatives of a function little f, so what does that mean? That is, the derivative of big F has to be little f, and so does the derivative of big G. That's also little f. That's what it means to be an antiderivative. Then, what can we say? Well then, g of x has to be f of x up to addition of a constant. For some constant c. In other words, big F and big G have to differ by at most a constant. They could be the same. Constant could be 0. If f and g are both antiderivatives, maybe they were just the same function. But at worst case scenario, if big F and big G are both antiderivatives and they're different from each other, worst case scenario, their difference is just some constant. So what that means is when we're looking at the set of all antiderivatives, you really just need to go to work on trying to find one antiderivative, because every other antiderivative is just some constant added to that original one. In other words, just some shift. If you think about the graph in the plane, it's just some vertical shift of one antiderivative. You vertically shift it, you can get all the other ones. So that's why it's not so confusing. Because if you do write down a single function, you can always get the set by just adding arbitrary constant c to get all the other antiderivatives. I do mention this as a note. Maybe I should just give a quick proof of this. What we're going to do is we're just going to look at the derivative of the difference. So we're going to start with the difference of the two functions. So I've got big G and big F as antiderivatives of little f. What's the derivative of this new function obtained by taking their difference? Well, it's just going to be g prime of x minus f prime of x. Both of those are equal to little f. So that's f of x minus f of x. And so that's 0. So we have that this function here, the difference of g and f, has 0 as its derivative. So what functions have 0 as their derivative? 0 everywhere. So the derivative is 0 everywhere. What kind of function must it be? Well, this has to be a constant function. So because the derivative is 0, then g of x minus f of x is constant. It's equal to c for some constant c. Therefore, just rearranging this, we get that g of x is equal to f of x plus c. And so there's the end of our proof. The fact that a function whose derivative is always 0 has to be a constant function, you may remember that was something we looked at back in differential calculus. If you've forgotten this result, then you can go ahead and have a look back in differential calculus, maybe your notes in there. It is related to the mean value theorem. So if you're trying to find exactly where this was justified, maybe look in the mean value theorem section. There's going to be an argument there that says if you have a function whose derivative is always 0, then the function had to have been constant. Okay, so what this means is that our work of finding or evaluating integrals is now reduced to computations of antiderivatives. We've got a notation that represents an antiderivative, this indefinite integral. It either represents the set of all antiderivatives or a single one. Depending on the context, it'll mean one or the other, but not to worry. If you're looking at a single antiderivative, you can always get all others by just adding an arbitrary constant, a plus c, for various values of c. Those give you various different antiderivatives. So, what does this mean? This means that we need to know our antiderivatives if we're going to have a chance of evaluating integrals using the fundamental theorem of calculus. Do we know antiderivatives of a lot of functions? Certainly we do. From Calculus 1, we computed lots of derivatives. And to find antiderivatives, you now just go backwards. So here's a table of integrals which you should definitely know. You should have these at your fingertips at all times. And they are, well, let's just look at a few of them. The antiderivative of e to the x, so we're looking at this one here, is e to the x, and then of course this plus c. So this is representing all possible antiderivatives. We start with 1 and add a plus c to get the rest of them. That was by that previous result that said any two antiderivatives differ by a constant. Why is the antiderivative of e to the x equal to e to the x? Well, because the derivative of e to the x is e to the x. So if you think about it this way, in this direction for all entries in this table, that's an integral. How are we discovering that integral? Well, we just have to look in this direction because that's the corresponding differentiation rule. So again, let's maybe look at another one here, this one over here. The antiderivative of cos of x dx is sine of x. Why is that? Well, it's because the derivative of sine of x is cos of x. So this table is completely constructed from our tables of derivatives, just writing them down in the opposite way. So this one would have come from this entry in our derivatives table. Derivative of sine of x is cos of x, therefore the antiderivative of cos of x is sine of x. That's how all these entries are found. And so make sure you do know all of these. Antiderivatives of sine, cosine, secant squared, cosecant squared, secant tangents, cosecant cotangents. This one here, 1 over x squared plus 1, the antiderivative of that is arctangent. There's similar ones for arcsine and arccosine, etc., which I haven't listed here, but this sort of forms the basis of the integrals you should know. We're going to take this a little bit further and then look at techniques for computing integrals or antiderivatives in general. We have these ones up at the top, which are just more general rules that say if you're trying to find the antiderivative of a constant times a function, you can always push the constant outside and just work on finding the antiderivative of the function. The antiderivative of the sum of two functions is just the sum of their antiderivatives. And the antiderivative of a constant is just a constant times x plus this arbitrary constant. And the reason, of course, is because the derivative of k times x is k. Okay, so let's do some examples. Find the following indefinite integrals. So we're looking for, these are indefinite integrals, so we're just looking to write down an antiderivative. So this is x to the negative 2/3. Maybe take a moment right now, pause the video, and try it for yourself. Okay, so I'll assume you've done it, so let's have a look. First thing to note is that I'm trying to find a function whose derivative is this. What should the exponent be? Well, when I take the derivative, whatever this exponent is, when I subtract 1 from it, I have to get negative 2/3. So if I add 1 to the negative 2/3, that gives me the exponent I want. So the power rule for differentiation says take 1 away from the exponent. So the antiderivative rule would say, well, add 1 to the exponent. Okay, now what do we do? Well, I can do a quick check. Is the derivative of this that? Well, I bring the 1/3 down. Oh, but I don't have a 1/3 in front. So I need to make sure I put a constant in front so that when the 1/3 comes down, it leaves me with the coefficient I want, which is 1. So I stick a 3 out front. So now the derivative is 1/3 comes down, that cancels to give me the 1 I want. And then take away 1 from the exponent. 1/3 minus 1 is negative 2/3. And so there's our antiderivative. And then we add r plus c. So now we have the set of all antiderivatives. How about this next one? Well, take a moment, pause the video, and try it out for yourself. Okay, let's have a look. The first thing I'm going to do is I'm going to expand out the integrand. Now I can go to work on the antiderivatives of each piece. There's a difference of two functions, so I just need to work out the antiderivatives of each piece and then take their difference. What about the first one? Well, what has a derivative of 3t squared? Well, that would be t cubed. What has a derivative of negative 4t to the 7th? Well, I can leave the negative 4 there and then just figure out what is the antiderivative of t to the 7th? What has derivative t to the 7th? Well, it would have to be t to the 8th. Because when I take that derivative, the exponent would change from an 8 to a 7. But the 8 would come down, so I have to make sure that I have a 1/8 in front to catch that 8 as it falls, because I need the 4 to be the coefficient of the result. And so I add a constant plus c, and then I can just do a bit of simplification. 4 times 1/8 is 1/2. And so there's our antiderivative. In this case, always do a quick check. Take the function that you've constructed and make sure its derivative is the integrand over here. So the derivative of t cubed, that's 3t squared. Yep, that gets the first piece. What about the derivative of negative 1/2 t to the 8? The 8 comes down, makes a 4, and that becomes a t to the 7th, so we get exactly what we wanted. So what about part C? Try it for yourself. Pause the video, give it a shot. Okay, let's have a look. So I'm going to expand it out. U cubed minus u squared plus 3u minus 3 du. And now I'm going to go to work on each piece. The antiderivative of u cubed has to be u to the 4th. The coefficient is a 1, so I have to make sure that I stick a 1/4 in front. And then I get a minus 1/3 u cubed. The antiderivative of 3u is 3/2 u squared minus a 3u plus our constant of integration, c. And do a quick check. Derivatives of each piece, make sure they get what you want. So 4 comes down, that's a 4/4 u cubed, yes. 3 comes down, that's a 3/3 u squared, yes. 2 comes down, that's a 3u, got it. And the derivative of u is just 1, so that becomes a -3. So we got it there. So pause the video now and try the next one for yourself. Okay, let's have a look. We're going to compute the antiderivatives of each one individually. So I'm just going to use some of the properties of antiderivatives to focus our attention on each piece. So I need to know these ones individually. What's the antiderivative of e to the v? Well, that would just be e to the v. What's the antiderivative of secant squared v? Well, now we have to think. What function do we know that has a derivative of secant squared v? We're having to think now back to differential calculus and all of those differentiation rules, all those differentiation formulas that we had in Calculus 1. We're going to have to try to remember them backwards now. So what function has a derivative of secant squared v? That would have been tangent. The derivative of tangent is secant squared. So the antiderivative of secant squared is tangent plus c. So you may have noticed that this was just one of those results we had listed in our table here. The antiderivative of secant squared is tangent because the derivative of tangent is secant squared. So that's what we're using here. And so there's our antiderivative. Try the last one for yourself, part E. Pause the video, go to work on this. Okay, so let's see, how do we do that? The antiderivative of cos z over 1 minus cos squared z dz. You may have found this to be slightly more difficult than the previous ones, and this is the nature of anti-differentiation. So if you think about derivatives, there's really only one way to compute a derivative. Just look at how the function's built up, apply the appropriate rule, break it down into smaller pieces, product rule, chain rule, quotient rule, etc. Once you get to those smaller pieces, then do it again and again. And each stage, you're just looking at how is the function built up, which rule, differentiation rule do I apply. For anti-differentiation, on the other hand, there isn't just one way to do it. There could be many different ways to solve or find the antiderivative. And you're just looking for one way to do this. So it does require good pattern recognition skills. And in some sense, it's a bit of an art to find antiderivatives. So how can we do it in this case? What am I looking for? Well, at this stage, I can't see right off the bat what function has this as its derivative. There's a quotient here, and there's a 1 minus cos squared z in the bottom. It looks kind of complicated, and I can't really spot what function has this as its derivative immediately. But maybe I can try to rewrite things. I know that the 1 minus cos squared in the bottom could always be written as sine squared. And, oh, okay, so now with the sine squared there, I could split that up as a 1 over sine and a cos over sine z. Now you may be thinking that, well, that doesn't look any simpler. But now, if we just rewrite it in terms of equivalent trigonometric functions, so 1 over sine is cosecant z, cos over sine is cotangent z dz. At this stage, we see that this is exactly the derivative of negative cosecant. So this is negative cosecant z plus our constant of integration. And so there we're done. Just take a peek back. That was this entry of the table. The antiderivative of cosecant cotangent is a negative cosecant. So that was the entry of the table that we used here. So what may look to be rather difficult at first, try to rewrite it in some ways, using some identities. Try to, massage your integral to get it into a form that you know how to deal with it. And this is going to be the standard pattern that we're going to use again and again and again. Try to massage the integrand to get it into a form you can deal with, and then find the antiderivative. So that was just a quick few examples to get us going in the process of finding antiderivatives. Over the coming weeks, we're going to look at lots of different techniques for coming up with antiderivatives.